In section 8.6, we address the applications of the normal distribution. So you will need that normal distribution table again to do the homework for this section also. So our first example starts off with, last fall, 2,500 students took the entrance exam at Tasmania University. The score of the exams have an approximately normal distribution with a mean of 52 and a standard deviation of 11. So what they're telling us with that information, and again, I like to get a picture of what's going on in my brain. So we know right smack in the middle is 52. And then with the standard deviation of 11, we can count up from there, adding on 11. So that would give me 63, 74, and 85. And to the left, we'll subtract off the deviations. So that would give us 52 minus 11, 41 minus 11, minus 11. So 19. So, okay, part A of the question. So sorry, let me write that down. So the mean is 52 and the standard deviation is 11. Part A is asking, estimate the percentage of students scoring 30 points or less. So we want the number of students who have a score that is less than 30. Well, the first thing we're going to have to do is go ahead and normalize that to a z-table. So we know that the z value would be that 30 minus the 52 all over 11. So that's the mean and the standard deviation. So that's a negative 22 over 11, which comes out to be a negative 2. So the question's asking us, what's the probability that a randomly chosen person has a z less than negative 2? Now I'll go to the table. So again, I go to negative 2.0. I then look up on the table what that comes out to be, and negative 2.0 comes out to be a probability of 0.0228, which is a 2.28% chance that a randomly chosen student at the university has a entrance exam score less than 30. So you can actually see the words helping this make some sense here. Part B on that question is asking us to estimate the percentage of students who have scores between 41 and 63. So the probability that 41 is less than our score, which is less than 63. So this is a donut hole problem. We're going to have to do both of them and then subtract their probabilities when we're all done. We'll have to normalize both of them. So z is going to be equal to 41 minus the 52 all over 11. Well, that's a negative 11 over 11. That's a negative 1. For the other score, the 63, 63 minus 52 over 11 comes out to be a positive 11 over 11, which is a positive 1. So this is basically asking us within one deviation. So negative 1 is less than z is less than a positive 1. So if we look both of them up, when we look up the negative 1, a negative 1 has a value of, lost it, sorry, 0.1587. So from the z table, this is 0.1587 is the probability. And the positive 1 has a probability of 0.8413. So our answer is going to be the difference between the two. Again, we're going between here and here. So we found this number and we found this number, but because the table reads to the left, we'll subtract the two. So 0.8413 minus 0.1587, sure enough, gives us the 0.6826. And if you remember when we started section 8.5, we talked about within one deviation being 68.26%. That's that same answer. So there's our 68.26%. Okay, example 2. So example 2 reads, according to the data released by the Chamber of Commerce for a certain city, the weekly wages of factory workers are normally distributed with a mean of 720 and a standard deviation of 60. So the mean is 720 and the standard deviation is $60. What's the probability that a factory worker selected at random from the city makes a weekly wage? And the first part A is asking for a weekly wage less than 720. So what's the probability that X is less than 720? Again, I'm going to get a handle on what's going on by drawing myself that normal curve. We know right in the middle is 720, and then we're going to count up by adding 60. So that'd be 780, 840, 900. And on this side, we'll subtract off the 60, so that would be 660, 600, and then over on this side, 540. Okay, well, wait a minute. I don't even need a Z table to do this one if they're asking if it's less than 720. 720 is the middle of this, and we know that the middle is 50%. So the probability that somebody makes less than 720 is going to be that 50%. If you go through the motions of finding the Z and then going to the Z table, you'll get the same exact answer. Part B says more than 912. So what's the probability that a randomly chosen worker has a salary more than 912? So what we're going to do is first translate that into a Z. The 912 is not one of these numbers, right? So I need to figure out what it is. And notice it's more than 3 deviations. So not very many people are out there on that end of the curve. So we'll do our 912 minus the 720 divided by the standard deviation of 60. If you do that, don't forget to put parentheses around your numerator. You get 3.2. So we're looking for the probability that a Z-score is greater than 3.2. Okay, that's a complement. We'll do 1 minus the probability that Z is less than 3.2. So look up 3.2 on my chart. 3.2 is 0.9993. So 99.93% of the data is to the left of 912. So 1 minus that means a randomly chosen worker in the factory having a salary greater than 912 is going to be 0.0007. That's 0.07% of the factory workers make more than 912. So not very many of them. And part C asks between 660 and 780. So this one's bound between two numbers. So 660 is less than X is less than that 780. First step, so find their Z values. So for the 660 minus the 720 divided by 60, and that one comes out to be a -1. So what you should be screaming at the computer right now is, wait, here's the 660, here's the 780. We should get the same answer that we did with the previous example because we're within 1 deviation. So that's that -1 coming in. And if we take the 780 minus the 720 divided by 60, we'll get a +1. So we know that we're between 1 deviation. And again, if you look them up, you're going to get that same 0.6826. What you would have to do individually is look up the -1, and the -1 came out to be, sorry, it's on the other paper. So from the table, the -1 is 0.1587. So if you look at the +1, you'll see that that one is at 0.8413. When you subtract the smaller from the larger, you'll end up with that same 68.26%.